Now, let me introduce about our project, which is projectile motion. What is projectile motion? Projectile motion is the motion of an object launched into the air, moving along a curved, parabolic path under the sole influence of gravity. To analyze this two-dimensional movement accurately, the flight must be separated into two completely independent components acting at the same time. The first component, which is horizontal component, x component. The motion is under constant acceleration, as equal to 0. Second component, vertical component, which is y component. The motion is at constant velocity, ay equal to negative gravity. Due to gravity, the object slows down at a rise until its vertical velocity becomes 0 at the maximum height. It then reverses direction and accelerates downward back to the ground, completing its total time of flight and reaching its full horizontal range.
The main objective of studying projectile motion is to understand how an object's position and velocity change throughout its motion. We also learn how to calculate important values such as the horizontal distance traveled, the vertical height reached, the total time the object remains in the air, and the maximum horizontal range. Now, I will explain the formulas used in projectile motion. Before applying the formulas, we first resolve the initial velocity into two components. The horizontal component is ux equals to u cos theta, where u is the initial velocity, theta is the angle of projection, ux is the horizontal velocity. Since there is no horizontal acceleration, this horizontal velocity remains constant throughout the motion. The horizontal displacement is calculated using x equals to u cos theta times t, where x is the horizontal distance and t is the time of motion. Next is the vertical component. The initial vertical velocity is uy equals to u sin theta. Unlike the horizontal motion, the vertical motion is affected by gravity. Therefore, the acceleration is a equals to negative g equals to negative 9.81 meters second square. The negative sign shows that gravity acts downward. The vertical displacement is calculated using y equals to u sin theta t minus half g t square. This equation determines the height of the projectile at any given time. The vertical velocity is v equals to u sin theta minus gt. This formula shows that the vertical velocity decreases as the projectile moves upward. At the highest point, the vertical velocity becomes 0. After reaching the maximum height, gravity causes the object to accelerate downward. The maximum height of the projectile is calculated using h equals to u square sin square theta over 2g. This formula tells us the highest point reached before the object starts falling. Next is the time of flight. The time of flight is t equals to 2u sin theta over g. This represents the total time the projectile stays in the air before returning to the same level from which it was launched. Finally, the horizontal range is calculated using r equals to u square sin 2 theta over g. The horizontal range is the total horizontal distance traveled by the projectile before it lands.
Now, let's move to the next slide, which is case study 1. During a school science competition, a team of students designed and launched a water rocket as part of physics experiment to study projectile motion. The rocket was launched from ground level with an initial velocity of 30 ms-1 at an angle of 40 Celsius above the horizontal. Assuming that air resistance and negligible and the only force acting on the rocket after launch is gravity, with an acceleration due to gravity of g equal to 9.81 ms-2, the motion of the rocket can be analyzed using the principle of projectile motion to determine the maximum height, time of flight, and horizontal range. First, we need to find the maximum height. At the highest speed of the flight, the final vertical velocity becomes 0, Vy equal to 0. We use Vy square equal to Uy square minus 2gs as the formula. Then, we apply the value into the formula to find S, and we got the last answer, which is S equal to 18.95 m. So the maximum height is 19.95 m. Next, we need to find time of flight. Total vertical net displacement is 0 as y equal to 0. We use sy equal to uyt minus 1 over 2 gt squared to find the value of t. And we got the last answer, which is t equal to 3.93 s. The last one, we find the horizontal range. We use r equal to uxt as the formula to find the r. And we got the answer, which is r equal to 90.32 n.
Now, we're gonna move on to our next study case. During a basketball training session, a player attempts a long distance shot from 5.5 meters away from the basket. The ball leaves the player's hands from a height of 2.1 meters with an initial speed of 10 meters per second at an angle of 48 degrees above the horizontal. The coach wants to determine the ball's maximum height, total time of flight, and horizontal distance traveled. In this analysis, we assume there is no air resistance, so the basketball is only affected by gravity after it is released. We use the standard gravitational acceleration of 9.81 meters per second squared. With these assumptions, we can use projectile motion equations to predict the ball's path and determine whether the shot will go into the basket. Now, I will explain the calculation used in our case study 2. First, we resolve the initial velocity into its horizontal and vertical components. The initial speed is 10 meters per second and the launch angle is 48 degrees. The horizontal component is calculated using cosine, which is ux equals 10 cos 48 degrees and ux equals 6.69 meter per second. And then the vertical component is calculated using sine, which is uy equals 10 sine 48 degree equals 7.43 meter per second. Next, we calculate the maximum height of the basketball. At the highest point, the vertical velocity becomes 0. Therefore, we use the equation v square equals u square minus 2gh. We substitute the values. 0 equals 743 square minus 2 times 9.81 times h. Then, we solve for h and got the final answer, h equals 2.81. Since the ball was released from a height of 2.1 meters, the maximum height of above the ground is h equals 2.1 plus 2.81 equals 4.91. Next, we find the total time of flight. The basketball lands on the ground, so the vertical displacement is minus 2.1 meters because it falls lower than when it was launched. We use the equation s equals ut minus 1 over 2 gt squared. Then, we use the values minus 2.1 equals 10 sine 48 degree t minus 1 over 2 times 9.81 t squared. Then, we rearrange the values, which is equals to 4.905 t squared minus 7.431 t minus 2.1 equals 0. Using the quadratic formula, we obtain the two answers. Since time cannot be negative, we take the positive value. Therefore, the total time of flight is t equals 1.76 seconds. Finally, we calculate the horizontal distance traveled. Since the horizontal velocity remains constant throughout the motion, we use r equals ux times t. Substituting the value, we get 11 cos 48 degree times 1.76. Final answer is 11.77 meters. From our calculation, the basketball reaches a maximum height of 4.91 meters, stays in the air for 1.76 seconds, and travels a horizontal distance of 11.77 meters. These results demonstrate how projectile's motion principles can be applied to analyze, predict, and trajectory of a basketball shot.
In conclusion, projectile motion is an important topic because it combines two different types of motion: horizontal motion with constant velocity and vertical motion with constant acceleration due to gravity. Although these two motions happen at the same time, they can be analyzed separately by using the appropriate equations. By understanding the formulas and knowing when to apply them, we can calculate the horizontal distance, vertical displacement, maximum height, time of flight, and horizontal range correctly. These concepts are not only useful for solving mathematics and physics problems, but also have many real-life applications, such as in sports, engineering, military science, and transportation.